A pleasant morning to one and all. I welcome you all to our Pharmacist GPAT Academy. Today here we are going to discuss about stereochemistry. Okay, the present topic here is stereochemistry. Well, coming to what is stereochemistry? The branch of science, the branch of chemistry dealing with the study of three-dimensional nature of a molecule is known as stereochemistry. Okay, stereochemistry is nothing but the study of arrangement of molecules around the atom in the three-dimensional manner. That is, studying the three-dimensional feature of a molecule is known as stereochemistry. Okay, well, coming to what is the significance of stereochemistry? If a compound is attached, if in a molecule, if the atoms are arranged in different forms, is there any changes that we observe? The major changes are, okay, let us learn about some of the different compounds. For example, D minus B glucose is metabolized by animals and fermented by yeast, unlike L glucose. Okay, the difference between D glucose and L glucose is nothing but the presence of as this naming is given according to the presence of OH while taking the reference molecule glyceraldehyde, which is a three-membered, which has a 3 carbon atoms. If the OH is present towards the right side, it is known as D compounds. If the OH is present towards the left side, those are known as L compounds. Okay, well, thus D-glucose is metabolized by animals and fermented by yeast, whereas L-glucose is not metabolized by the animals. Okay, next minus adrenaline is more hormonal active than plus adrenaline. Okay, minus adrenaline has more hormonal activity. These are the two isomers. It is minus form, this is plus form. There is a more difference in the hormonal activity when compared to plus form. Next is nicotine. Minus nicotine is more poisonous than plus nicotine. These are the two isomers where minus form is more poisonous than plus form. Okay. Next, coming to concept of chirality. Before knowing about stereochemistry, the first major concept that has to be learned in stereochemistry is chirality or asymmetry. An object that is not superimposable on its mirror image is called chiral and is unsymmetrical, while the object that is superimposable on its mirror image is called achiral and is symmetrical. Okay, well, coming to the concept of chirality, what happens is that an object that is non-superimposable, that is here, see, this is the object around is superimposed, they are non-superimposable. Okay, object is turned around and then placed over the image. Object is turned around and placed over the image. Object image have different orientations, so they seem to be superimposed, whereas actually they are non-superimposable. In this diagram, these two are the explanation of this. Whereas here what happens is that correct way of superimposition and incorrect way of superimposition. Okay. Chirality is nothing but, in our chemistry terms, if a carbon is attached to 4 different groups, then that carbon is known as chiral carbon. Chiral carbon, that is a carbon attached to 4 different groups, is known as a chiral carbon. Okay, such molecules, such carbons are known as chiral and they are non-symmetrical because they are attached to different groups. Symmetry is not observed. Okay, for example, in this diagram, it is an unsymmetrical object and this is the image. Incorrect way of superimposition. Okay, if this is turned and superimposed on it, they look like they are superimposing, but they are not. The correct way of superimposing is that taking this and straightly placing over it. Okay, object is picked up as it is and then placed over the image. Both objects have same orientation. These are non-superimposable. Okay. The examples of non-superimposable are our hands. Okay. This is general explanation, and while coming to the chemistry, a carbon attached to 4 different groups. Such kind of carbon is known as a chiral carbon. Next, coming to chirality in organic molecules, enantiomers and diastereomers. Based on this superimposability, the organic molecules, that is, there are 2 types of isomers, enantiomers and diastereomers. The stereoisomer of a compound, which are non-superimposable mirror images of each other, are termed as enantiomers. Okay, enantiomers are non-superimposable mirror images. A molecule with one stereogenic center always exists in an enantiomeric form. Okay, stereogenic center is nothing but a chiral center. As I mentioned earlier, a carbon attached to 4 different groups is termed as a chiral carbon. In enantiomer, there is a possibility of presence of at least one chiral center. Okay, these stereoisomers are enantiomers are non-superimposable mirror images, whereas the stereoisomers of a compound which are not mirror images of each other are termed as diastereomers. The diastereomers exist only when a compound has 2 or more stereogenic center. The difference between enantiomers and diastereomers are these are non-superimposable mirror images are enantiomers, whereas diastereomers are not mirror images. Non-superimposable mirror images are enantiomers, whereas diastereomers are not mirror images. Enantiomers contain at least one stereogenic center. Diastereomers exist when there are possibility of presence of more than 2 or more stereogenic centers. Stereogenic centers are nothing but chiral centers. Okay. Next, coming to the number of stereoisomers of a compound. Okay. How many if a compound is given, and if we'll ask how many isomers, stereoisomers are possible of a compound, then there is a formula, that is number of stereoisomers are equal to 2 power n, where n is the number of chiral center present in the compound. Okay, the number of stereoisomers present in a compound is given by the formula 2 power n, where n is number of chiral center. For example, consider lactic acid. It has 1 chiral center, therefore 2 power 1 equal to 2, that is it has 2 stereoisomers. Next, coming to meso compounds. Okay, enantiomers, diastereomers, now meso compounds. A compound having stereogenic center but optically inactive, a chiral, due to presence of plane of symmetry, is termed as meso compounds or a mesoform. Okay, actually if a compound have stereogenic center, then it is said to be chiral. But what happens is that in this meso compounds they have a chiral center, but due to the presence of symmetry they are optically inactive. Okay, in meso compounds the plane divides the molecules into halves that are mirror images of each other. The internal compensation makes meso compounds optically inactive. Okay, consider a 4-membered compound. Okay, if it is divided into half, what happens? The upper 2 carbons and lower 2 carbons, these are symmetrical carbons, that is both carbons show both are like same, so the plane of symmetry is there. So is termed, such compounds are termed as meso compounds, which are optically inactive due to the presence of plane of symmetry. Due to the presence of this plane of symmetry between the 4 carbons, that is if consider 4 carbon atom, 4 carbon chain, and these 2 carbons are having similar composition and these 2 carbons are having similar composition due to the plane of symmetry, such kind of compounds are known as meso compounds, because due to the plane of symmetry the upper molecule and lower molecules, as they are same, they are optically inactive even though they contains a stereogenic center. Such kind of compounds are known as meso compounds. Next, coming to optical activity. polarized light will rotate the plane of light. The compounds exhibiting such a behavior are termed optically active. Okay. The compounds exhibiting such a behavior are termed to be optically active. Okay, optical activity is nothing but when a compound containing a chiral center is placed in a path where a plane polarized light passes through the substance, then this compound will have the ability to rotate the plane polarized light. Such compounds exhibiting such behavior is termed as optical activity. A compound rotating the plane polarized light towards the right, that is clockwise, is known as dextrorotatory, whereas that is towards the right, dextrorotatory, toward the left, revorotatory, and it is minus. Levorotatory is if it is levorotatory, it is designated by minus. If it is dextrorotatory, it is designated by the sign plus. Okay, this is a two by optical activity how we will differentiate between the isomers. Next, coming to specific rotation. What do you mean by specific rotation? Specific rotation is designated by the symbol alpha, is a rotation caused by the sample at a concentration of 1 gram per ml in a sample tube of length 1 dm, that is 10 centimeter or 1 decimeter. The value of specific rotation depends on the concentration of the sample, its structure, the wavelength of the source, temperature, length of the sample tube, and solvent. Okay, specific rotation is nothing but the rotation caused by the sample at a concentration, that is the sample concentration would be 1 gram per ml, which is present in the sample tube of length 1 decimeter, and such is known as specific rotation of that specific sample. And this specific rotation mainly depends upon the concentration of the sample, its structure, wavelength of light source, temperature, length of the sample tube, and solvent. Next, coming to one of the important topic, that is racemic mixture. What do you mean by a racemic mixture? A mixture containing equal amounts of pairs of enantiomers is termed as racemic mixture or racemic modification. A racemic mixture is optically inactive. Okay, a pair or a mixture containing equal amount of enantiomers is known as racemic mixture. A racemic mixture is optically inactive. Why a racemic mixture is optically inactive? Because the pair of enantiomers present, that is a pair of enantiomers. Suppose we have a plus compound and minus compound. The plus compound causes some rotation, and this minus compound also causes some rotation. Okay, that is specific rotation due to the presence of a chiral center. Then what happens? Actually, enantiomers are optically active as they contain at least one stereogenic center. But due to the presence of a pair of isomers, that is the presence of a plus isomer and a minus isomer, what happens is that the specific rotation caused by the opposite sign enantiomers will cancel up, resulting in the resulting specific rotation will be 0. Okay. Nothing. It can be simply explained as a racemic mixture is nothing but it contains enantiomers. As I discussed earlier, enantiomers show specific rotation, but due to the presence of that is a plus isomer and minus isomer in equal amounts, what happens is that the resulting specific rotation will be 0, as a resulting specific rotation of this enantiomeric mixture will be 0, as this racemic mixture does not exhibit specific rotation. Okay, as the enantiomeric exhibits specific rotation in opposite directions, the specific rotation value of two isomers cancel each other, resulting in 0 optical activity. The racemic mixture is denoted by plus, for example, plus lactic acid. Next, coming to stereoisomers and their optical activity. Enantiomers show identical physical properties, but they may differ in their smell. Diastereomers show different physical properties. For example, melting point enantiomers have identical physical properties, whereas diastereomers show different physical properties like melting point, boiling point, solubility, refractive index, density, etc. Next, enantiomers show specific rotation value but rotate the plane polarized light in opposite directions. Okay, enantiomers show specific rotation value but rotate the plane polarized light in opposite direction. Diastereomers differ in their specific rotation values. Diastereomers have different specific rotation values. The third point is that enantiomers exhibit identical chemical properties except in their reactions with optically active reagent. Okay, enantiomers exhibit identical chemical properties except in their reactions with optically active reagents. Diastereomers show different chemical properties. Diastereomers show different physical and chemical properties, whereas enantiomers have identical physical properties and identical chemical properties, but exception is that reaction with only optically active reagents. A racemic mixture is optically inactive due to external composition. Okay, due to the composition in the racemic mixture, that is presence of equal amount of plus forms and minus forms, the resulting specific rotation will be zero. Hence, these are optically inactive. A stereoisomer with a plane of symmetry, that is meso compounds, is optically inactive due to the presence of plane of symmetry. In meso structure, one half of the molecule is same as that of mirror image of the other half. Okay. Next, coming to absolute configuration, that is R and S configuration. The most important task of our organic chemistry is to assign configuration to stereoisomers. Although we can distinguish enantiomers by the sign of optical rotation, assigning the configuration to plus and minus isomers is not easy. Next, coming to assigning of R and S configuration. First of all, a compound is written in the Fischer projection. Next, here see, for example, this compound where a carbon is attached to 4 different molecules. Okay, 4 different molecules. These 4 are different, are halogens. So what happens? First of all, we have to write the molecules in the Fischer projection. Next, we have to give the numbering to the molecules based upon the atomic number. That is, highest atomic number compounds are given 1, and next lowest, that is highest atomic number are given the highest numbers, and lower are given lower numbers. Okay, in these groups or atoms are ordered in clockwise manner. The absolute configuration assigned is R. Okay, as I told earlier, clockwise rotation R and anti-clockwise S. Okay, see here, for example, the iodine is highest, next bromine, next chlorine, next iodine. So it indicates that 1 to 2. See, these are the numbers given. So from 1 to, the rotation is from 1 to like this. So it is a clockwise. Whereas here what happens? The oxygen is given first priority, followed by nitrogen, followed by carbon, last priority to hydrogen. So it shows that it rotates like this. That is anti-clockwise. Hence given R configuration. Okay. This is how R and S configurations are assigned to individual moieties. First of all, they have to be written in Fischer projection. The second point is that they have to be assigned based on the atomic number. That is, highest atomic number containing atoms are given first numbers, followed by next highest, second by followed by next highest number. Okay, and based upon the rotation, that is 1 to 2, if it is clockwise, it is given R configuration. If it is anti-clockwise, these are given S configuration. Next, coming to relative configuration, D and L nomenclature. As I discussed in the previous classes regarding the naming of our carbohydrates, the D and L configuration is mainly based upon the parent molecule, that is glyceraldehyde, which is a 3-carbon containing compound. If the OH is present towards the right side, then it is known as a D-glyceraldehyde. If it is present towards the left side, it is known as L-glyceraldehyde. Based upon this parent moiety, the different compounds are given, are assigned as D and L forms based on the presence of OH groups towards the right or left side. Next, coming to geometrical isomerism. The compounds having similar molecular formula but different arrangement of atoms or groups in space around the double bonds are called geometrical isomers, and the phenomenon is known as geometrical isomerism. Okay, geometrical isomers are those compounds just having similar molecular formula but difference in the arrangement of groups in space around the double bonds are called as geometrical isomers, and the phenomenon is called as geometrical isomerism. The geometrical isomerism arises due to restriction in the rotation around carbon-carbon double bonds. Okay, this geometrical isomerism is mainly seen in alkenes, where there will be a restriction in carbon-carbon double bond rotation. Next, coming to necessity and sufficient condition for geometrical isomerism. An alkene of a type AB C double bond CXY exhibit geometrical isomerism if A not equal to B and X not equal to Y. In alkenes, if either of the double bonded carbon is attached to identical groups or atoms, geometrical isomerism will be existed. Okay, for example, A and B and X or Y should not be equal. If any such equal or same molecules are attached, then geometrical isomerism will not be seen in such kind of alkene moieties. Next, coming to cis and trans systems. This system is used for designing the alkenes in which two olefinic carbons having at least one similar group or atom present on them. In the previous slides, as I told, that if it contains equal that is same atoms, then their geometrical isomerism is not seen. So for such cases and trans, for example, these compounds, the identical atoms are present opposite sides, so it is known as cis. If the identical atoms are present on the same side of the plane, then it is known as cis. If the identical atoms are present on the opposite plane, it is known as trans. This is a trans molecule. This is a cis molecule, that is present on the same side of the plane. Identical atoms, if they are present on the same side of the plane, it is known as cis. If the identical atoms are present on the opposite sides of the plane, it is known as trans. In the term cis is used when two similar atoms or groups are present on the same side across the double bond, and the term trans is used when the two similar atoms or groups are present on the opposite side and across the double bond. Okay, as I discussed earlier, same side cis, opposite sides trans. Next, coming to EZ system, that is anti-Gagan and Jusamen system. The alkenes of the type AB C double bond CXY exhibit geometrical isomerism, but they cannot be classified as cis or trans isomers as all the substances attached to olefinic carbons are different. Okay, in cis they should be identical atoms. If if the four molecules attached to two double bonded olefinic carbons are different, then EZ system is used. Okay, if the higher priority groups are present on the same side across the double bond, the geometrical isomers is said to be Z. The higher priority groups are present on the opposite sides across the double bonds. The geometrical isomer is said to have E configuration, that is anti-Gagan opposite, Jusamen same side. Okay, this is the example. C double bond. See, first of all, The, the it is known as anti-Gaussian, that is present on the opposite planes. The higher priority numbers, that is the priority here a C double. For example, consider this compound. Here we have a olefinic carbon atom, C double bonded C carbon atom, which is attached to 4 different atoms. Okay, here the number is given based upon the atomic number, that is the highest atomic number is given highest priority than lower priority. Here obviously for this the fluorine first number and hydrogen is given second number. Okay, as here if we see these are different, 1 and 2 are different, so it is known as, that is opposite sides contain the highest priority number, so it is known as anti-Gaussian. Well, coming to here to this example, here see the 1 2 bromine 1 oxygen, sorry, bromine 1 and oxygen 2. So here if we see higher priority numbers are present on the same side of the plane and lower priority numbers are present on the same side of the plane. This is known as Zusammen, that is presence of highest priority numbers on the same side of the plane. That is known as Zusammen, that is same side. E stands for anti-Gaussian, opposite sides. Mainly here the naming is given based upon the presence of higher atomic number containing compounds towards the same side or opposite sides of the plane. Based on that, the atoms are given or assigned with E and Z system. Okay. Conformation. Next, coming to conformations. In alkanes, whereas in the previous geometrical isomers is seen for alkenes. For alkanes, we will see conformations. In alkanes, the carbon atoms are connected through single bonds. The atoms connected by single bonds can rotate about that bond without breaking it, and the energy required for this is very low. Molecules possess kinetic energy due to the state of continuous motion. The energy is transferred among the molecules during collisions and is sufficient to bring about rotation about single bond, and for this reason the rotation is termed free rotation. Conformations are seen for alkanes. Okay, on the whole we can say that due to rotation between easy rotation between C single bond C between the two atoms. Next, coming to conformations of ethane. In the case of ethane molecule, the free rotation above sigma bond result in two conformations, namely staggered and eclipsed conformation. Here it is a staggered, here it is eclipsed, here it is again staggered. Okay, in staggered conformation, the carbon hydrogen bond on each carbon are at maximum distance, thus have minimum repulsions. Okay, in staggered conformation, the distance between the carbon and hydrogen bond is maximum. Okay, CH bonds on each carbon atom, the distance between the CH bond between the, so there are less repulsions. In eclipsed form, the carbon hydrogen bond on each side are at minimum distance. So that's why very close to each other and thus experience maximum repulsion. So maximum repulsions are seen at eclipsed form, minimum repulsions are seen at staggered form. Next, coming to representation of conformations. How these conformations, that is staggered, eclipsed, are represented. Sohor's projection. In Sohor's projection, the two carbon atoms are attached to sigma bonds are represented by points. Okay, are represented by points where 4 lines intersect. Where these 4 lines intersect. The bond through which two carbon atoms are joined is considered in the plane where the atoms attached to the carbon may be above or below. Okay, the carbon attached to the bond through which two carbons are joined is considered in the plane where the atoms are attached where two carbons are attached by sigma bonds, and these are hydrogens which are attached above and to the below the planes, see respectively. If here it is present above, here it is below the plane, and this hydrogen is above the plane and this hydrogen is below the plane. It is staggered form. Whereas in eclipsed form, what happens? See, here this carbon is above the plane. The two carbon attached through sigma bonds, same as eclipse form, and this rotation occurs. As a result, this hydrogen will come above the plane, and there is a minimum distance between this two carbon hydrogen bond. As a result, it absorbs maximum repulsion, whereas here this is present above the plane and this is present below the plane. As a result, the distance between these two is maximum, hence minimum repulsions. This is the point which has been discussed in the previous slides. Next, coming to Newman projection. In Newman projection, a dot or a circle represents the two carbons attached through sigma bonds. The dots represent the front carbon, whereas the circle represents the rear carbon. The dots represent the front carbon, whereas the circle represents the rear carbon. That represents the two carbon attached to sigma bonds. The three bonds attached to front carbon are represented to full lines, whereas the three bonds attached to rear carbons are represented by line arising from the surface of the circle. Thus, the staggered and eclipse form of ethane can be represented as shown in the structures. The structures are given in the next slide. Okay, here see. Staggered conformation, it is an eclipsed conformation. The circle is rear carbon. This is front carbon. Okay. This is front carbon and the circle represents the rear carbon. Here, the hydrogens are attached. This is a staggered form. Whereas, if it rotates to 60 degrees, what happens is that this hydrogen will move, and here, see, the hydrogens, there is very minimum distance between the first carbon containing hydrogen and the second carbon hydrogen. That is, here maximum repulsion due to minimum distance. Here, maximum no repulsions because there is a maximum distance between these two carbons. And when again it is rotated, this form is rotated to 60 degrees, it forms staggered. Again rotation for 60 degrees, it forms eclipse. Okay, this is the representation of Newman's projection of ethane conformation, representation of ethane conformers by using Newman's projection, where the circle represents the rear carbon and the lines represents the front carbon. The eclipsed, difference between eclipsed form and staggered form. This is the whole topic which are discussed in our stereochemistry topics. The above discussed topics are very important in our stereochemistry. Okay, these are all the important topics regarding the stereochemistry are discussed in this class. Okay, thank you.